On this 2015 to 2025 F-150 with the 2.7 EcoBoost, P0300 is a random misfire code. In plain language, the engine may be misfiring without the fault being isolated to one specific cylinder. The truck may idle rough, stumble, feel down on power, or set the check engine light. Broadly, a random misfire can come from possible ignition, fuel, air and vacuum, mechanical, exhaust, wiring, connector, or control input issues. For this episode, the safe path is not a P0300 specific pinpoint routine. Treat this as the diagnostic method that keeps you from guessing. Confirm the concern is present. Do the basic checks first. Sort out any supporting codes in the right order. Then, test circuits and components correctly before making any repair decision. Start by assuming the concern is present unless your testing proves otherwise. If the misfire is not acting up during the test, do not replace modules or parts just because a diagnostic path could eventually point that way. Before getting deep, do the preliminary checks.
Look for obvious issues that match the customer's complaint. Check for related OASIS or TSB information if it is available.
Look closely at any previous repairs, because an incorrectly completed repair can create the concern you are chasing now. Then make sure the vehicle is electrically healthy. Check the battery and charging system and verify battery SOC is greater than 70% before beginning diagnostics. Next, scan all network modules for system or symptom codes that relate to the concern. Do not turn this into a long code list in your head. Use the codes as routing information. If other codes are present, check what they mean first. Diagnose circuit-related codes before system or performance-type codes. And if you have multiple circuit faults, look for a shared cause, like a common power feed or ground path, instead of treating each one like a separate failure. Now work through the physical checks in order. Inspect wiring harnesses for damage, chafing, and routing. Check fuses, electrical circuits, and connectors for continuity and correct installation. Make sure components are actually connected. On a random misfire, do not skip the air, fuel, fluid, and exhaust basics. Inspect vacuum lines and the air intake for leaks, routing problems, or restrictions. Check hoses for damage, leaks, blockage, and routing. Check fuel quality for octane, contamination, and seasonal blend. Inspect the fuel tank and fuel lines for damage, leaks, and routing. Check coolant level and quality with the engine at the correct operating temperature. Check oil level and quality for contamination and maintenance condition, and inspect the exhaust for damage, restrictions, and routing. When you connect test equipment or jumper wires at terminals, use Rotunda Flex Probes NUD 105R025F or Terminal Probe Kit 418-SO35 or an equivalent terminal safe method. The point is to avoid spreading or damaging the pins while you test. Check male to female terminal fit with the mating pin and feel for normal separation force. A damaged pin will have very low separation force. If a hard shell, pin guide, or retainer adds drag on small terminals, remove what is needed so the terminal fit can be judged correctly. Damaged connectors, pins, or terminals are repaired by replacing the damaged connector, pin, or terminal. Then use the scan tool for PID input values, output states, and diagnostic states. Use the data logger for accurate testing without unnecessary disassembly, and use output state commands where they are available. For module-related checks, understand how the function is supposed to operate before condemning anything. Make sure programmable parameters are set correctly for the function you are testing. Resolve the DTC first, as directed by the diagnostic path. Test all inputs, both hardwired and networked. Then, test outputs. Check for module software updates. If you use output state control and the module output works normally, that points you back toward analyzing the inputs. Do not replace a module because the testing was incomplete, and do not apply power or ground directly to module-switched components with jumper wires unless the test specifically tells you to do that. When checking power-providing circuits, do not rely on voltage measured with the intended load disconnected. That will usually only tell you if the circuit is open. It will not prove the circuit can carry current. For circuits carrying approximately 200 to 1000 milliamps, load the circuit with a 250 to 350 milliamp test light and measure voltage with the DMM while the light is connected. If voltage drops during that loaded test, you are looking at excessive circuit resistance. For conductor sizes 24 gauge, 0.5 millimeters or smaller, use a 250 to 350 milliamp test light to load the circuit when appropriate. That small conductor guidance applies to circuits generally carrying approximately 1000 milliamps, 1 ampere or less. For the heavier side, conductors 20 gauge, 0.8 millimeters or larger generally carry 1 ampere, 1000 milliamps or more. For circuits carrying more than 1 ampere, load the circuit with a device that requires similar current, such as a brake light bulb. Again, a voltage reduction during loading indicates excessive resistance. For higher current circuits, voltage drop is the better test method. For ground-providing circuits, measure voltage drop while the component is operating or while you are attempting to operate it. If you use an ohm meter on ground circuits, disconnect the battery first, because normal voltage across body and chassis grounds can corrupt the reading. When checking resistance or continuity, most wiring harness circuits should be less than 2 ohms. Keep the meter limits in mind too. A standard DMM ohm meter has a low resistance resolution of approximately 0.1 ohm and is generally accurate for circuits carrying less than approximately 5 amperes. If you are checking resistance, reverse the DMM leads and watch the measurement. Unless the circuit contains a semiconductor, the reading should not change. If it does, the test result is not valid. To check for unintended continuity to ground, disconnect both ends of the suspect circuit and measure from that circuit to ground. Expect greater than 10,000 ohms. To check for unintended continuity to another unpowered circuit, disconnect both ends of both circuits and measure between them. Expect greater than 10,000 ohms. To check for unintended continuity to a powered circuit, disconnect both ends of the suspect circuit, turn on ignition, run power, and measure voltage from the suspect circuit to ground. Back probing has a place, but use it only when the circuit must be tested under real operating conditions, when a voltage drop method is required, or when opening the circuit could change module failure behavior. In voltage drop testing, every circuit will show some loss. Expect less than 5% of circuit operating voltage. Do not force probes into connectors. Use back probes designed for the job so you make contact without damaging the terminal. Back probing is the wrong move for a single-point voltage check where 0 volts is possible, because you cannot tell a true 0 from a bad probe contact. Disconnect the circuit and test normally. It is also the wrong move for ohm meter continuity or open circuit checks between 2 points. Disconnect and isolate the circuit, then test it normally. When jumper wires are needed for circuit analysis, always use fused jumpers. The recommended universal testing jumper wire fuse is 5 amperes or less, with a larger fuse only when the load requires it. Use flex probes or equivalent to protect terminals, but do not use flex probes to power cooling fans, blower motors, or other high current devices. Follow the test directions carefully, so a wrong jumper connection does not damage the component or harness. Do not repair a circuit by overlaying a new wire in parallel with the old one, unless you fully understand why the original circuit failed. Find the fault, examine it, repair the root cause, and repair adjacent damaged wiring. For voltage drop measurements, connect the voltmeter at the beginning and end of the suspect circuit, then operate or attempt to operate the circuit. Power has to be on and available to flow. Follow conventional current flow with the meter polarity. A 0-volt reading means you may have bad meter connections where the component is not turned on. A small voltage loss is normal. Greater than 0.5 volts indicates abnormal voltage loss, and high voltage drop points toward high resistance in wires or connectors. For a voltage in, voltage out test, connect the negative meter lead to ground or battery negative. Operate or attempt to operate the circuit. Measure the power side of the load first, then the negative side. The power side should be within 0.5 volts of battery voltage. The ground side should be greater than 0 volts, but less than 0.5 volts. A reading of 0 volts, or source voltage, indicates an open circuit. The takeaway on P0300 is simple. Do not let a random misfire code turn into random parts replacement. Confirm the concern, clear the basic checks, use other codes for direction, and prove the circuit or system fault with loaded testing before you call the repair. For more diagnostic training, Visit stepdiagnostics.com.